Hey, good morning, good afternoon, wherever you are. Welcome to the 5G Connected Edge Cloud tutorial. Wish we could be doing this in person. I think we all agree with that, but because of we may have a lack of personal touch here, but we're just going to overwhelm you with parallel streams of information. So just a couple of bookkeeping things here. You'll see a couple of links. One that you can go get all the tutorial information. That includes pointers to open source online versions of the two books you see here, which are where a lot of the material that's in the tutorial comes from. So unfortunately, in only 3 hours, it's a bit of a high level treatment of the topic, but you can go find more depth and other information there. And there's actually also some online programming exercises if you want to go that route. We also have a Slack channel, and I encourage you to make active and aggressive use of it. We've got several of us bringing this to you. I'm going to be doing the slides, but I know Oz and Nate and Jennifer are online, and I haven't checked, but maybe Sachin is there now too. They're going to be commenting on what I'm talking about, offering their view of it as well, and their insights, and answering your questions. So it's going to be kind of hard for me to juggle all of the Slack and the slides, but with their help, I'm hoping that we can have a pretty interactive session here. So please do make yourself known, ask questions, and so on there. Before we get going, let me just have Nate and I know Nate and Jen and Oz are on. If you could just show us your faces and say hi.
Hi, Nate Foster. Thrilled that you all are here and looking forward to spending the day with you.
Hi, Jen Rexford. Hello, welcome.
So Oz, you there?
Hi, Oz and I, welcome.
Great, thanks, Oz. So I don't think Nick's going to be joining us. I don't know if those of you have heard the news. Nick has temporarily left Stanford. He's at Intel doing big things with programmable data planes and switches. So all is good there, but I don't think he's going to be able to. I don't think he's going to make this. And Sachin, I think he was in earlier, and I'm hoping he gets back as well. So we got tons of expertise. We've got well, let me just get into just the plan so that we can have a sense of where this is all going. So for me, the beginning of this was several years ago at the Open Networking Foundation, who does open source solutions and building blocks and platforms and so on for SDN, started to get into the mobile space. And I was trying to learn it so I could come up to speed. We have a really great engineering team, but pretty much all of them come from the cloud space, the more traditional internet backgrounds. Practically none of them came from the mobile cellular network, and certainly I didn't. I mean, I've been in networking for a long time, and I knew virtually nothing about it. And my first exposure was just an overwhelming wall of acronyms. And I'm sure anyone trying to learn the internet has the same experience, but so I just started digging, and Oz has been on the team as well, and he's the 4G 5G expert, and he started to teach it to me, and I started to write it down and tried to explain it to others, and at one point helped a little bit with Nate and Jen coming up to speed on it. And that's kind of the genesis behind the books and these slides, and one of the major intents of this tutorial, which is I'd always kind of thought of the cellular network is there's a lot of great information theory going on there. But from my point of view, it was just yet another one of many access networks. And I didn't really bother myself with learning the internals of it. But with 5G, it's becoming so incredibly important. I don't think you can continue to just abstract it away. And more than that, it's the nature of the mobile network is changing, and it's merging with the cloud. And that's kind of what this tutorial is about. But to get there, you got to kind of deconstruct 5G so you understand what all of the building blocks are. And as we deconstruct it, we're not going to go in the information theory, coding theory direction at all. I'm completely unable to do that. But what I can do is try to kind of shine a systems light on what the network is about. And part of that, what is the network, the 5G network about, is identifying the open source building blocks. it's a new day in networking. Everything is available as open source, and that includes what had been a very closed proprietary world, which is the cellular network. But there's a lot of open source building blocks, and we're doing a lot of them at ONF. And because we have the building blocks, it's easy to stop there and say, okay, go find this building block, go find that one, whatever interests you. But I think one of the really important things we're going to try to do in this tutorial is show you how they all fit back together. Your interests, and the reason you're here, may be very narrow. You may have a particular, I'm going to guess a lot of you are looking for research projects, and you may have something very narrow in mind, but I think it's really important here to see the end-to-end perspective. And that's going to be both up and down the software stack. So we're going to look end to end, top to bottom, left to right. We're not going to, it is a complete software stack. And it's actually quite a bit different than the software stack we were perhaps all raised on with the TCP/IP stack. And we're going to look at this from an innovation research point of view, but all the way to real world deployment. So one of the things that we've been doing is putting all these building blocks back together so that we have an end-to-end 5G edge cloud. And so that edge cloud has been deployed. We are partnered with a lot of major carriers and other cloud providers, Google, Facebook, Deutsche Telekom, NTT, the list goes on. And they are all just as interested in the uptake of all of this stuff as those of us on the more academic side are interested in generating new ideas. So that's a really critical part of all of this. And finally, it's great that we have people doing a lot of active research here, and we're gonna, they're gonna be commenting as I go along, and there's gonna be time at the end to come back and open up the floor, just let them talk about their experiences doing research and where they see the opportunities. And so with that, well, I got a couple more intro slides here. And I'm going to start with this general picture, which I actually came to understand to be a Rorschach ink blob test. You look at it and different people see different things. When I made this image, or cribbed it from O's, I forget which it was, I had a very internet-centric view of what it said, because I thought, okay, that's the internet, I know that, and it's got some access networks, and some of them happen to be cell access networks. But if you kind of turn this picture the other way, the RAN, the radio access network, is a global network. There's a unique identifier for every device on the RAN, and it doesn't matter whether you're in London or Tokyo or San Francisco, you can reach all of those, pretty much reach all of those other devices. It's like an IP address, but it's at the device level. And yeah, while it's true that a certain set of base stations are connected back into some aggregation points, and that might be limited to, say, a metro area, from that point of view, the internet backbone could have been anybody's backbone. And in its history, it was different backbones interconnecting all of those metro areas and creating a global network. And so if you really think of the RAN as another global network, like the internet as a global network, and now these two networks are fusing in a way they had not before, that's where the real opportunity here is. So I've actually kind of hinted at this. The history of the mobile cellular network is as old as the internet. It's 40 years old, and you've heard of the different generations. 3G introduced broadband, 4G made it faster. 5G is going to make it faster as well, but there's a lot more to it, and we'll talk about what some of that is. But the flip side of it has been, it has in its history largely been extremely opaque to everyone but the vendors that were producing hardware. There is a standards body, so there are public standards available. If you can go read 1,000 pages of standards and then understand the concepts, the power to you, but it's a pretty tough slog. But what's really important here is that this is now becoming open, and there's open source versions of pretty much all of this. And that's what we're gonna focus on. So I mentioned that 5G is about more than going faster. It certainly is about going faster at higher rates, so both in the aggregate and peak rates between any pair of devices. But it is also about scaling up the number of devices that are being connected. And that has that's not only a density thing. There's, on the previous slide, you may have seen that each of these generations is a 10-year plan. we are at the beginning of the 5G 10 years. And so this is by no means realized. It's just what's on everybody's to-do list. So it's not only high density, but it's also extremely low energy for many of these devices. And as a consequence, they have very low complexity. And so you have to deal with, powerful devices connected by 5G and Internet of Things devices as well. And the final, just if this is not going to be hard enough, the final objective is that this all happens at extremely low latencies. And more important than the low latency, I think, is the high availability that, you've got 5 nines worth of, you're meeting your latency goals 5 nines of the time. And that's important to mission critical applications, which is one of the set of applications we want to support. And at the same time, things are moving very fast. And the mobility aspect has been ramped up. So these are the goals of 5G. And like I said, it's about much more than going faster. And in fact, let me try to tie that back to the edge cloud. This is what's happening independent of 5G, but this is where these two come together really well. So you're probably aware that functionality is moving from the data center and it's moving out to the edge, so it'd be closer to the end user devices. And there's a lot of reasons for that low latency, high bandwidth at the edge. Immersive user interfaces, one set of examples, everything, Internet of Things, autonomous vehicles, and so on, coordinated robots, another domain of application. If you've not heard the buzzword, you should be able to speak Industry 4.0, smart factories, smart warehouses, smart retail, and so on. But it sort of all begs the question, though, is where to the edge? And if you are a traditional telco, then you would point to the aggregation points you already had in place. That's where the access networks were already implemented. That earlier picture I had, everything was aggregated back. And that's certainly one possibility. And you can be absolutely certain that the large telcos or telcos in general are working very hard to do this. But there's another opportunity, which is the one that we're going to focus a little bit more on, which is that you can now bring 5G on premises into your enterprise, into your campus, and the other parts of it actually live in the cloud. So we don't have to think about this as it's in the domain entirely of network operators. This is now technology we can all use, not that much different than that we use Wi-Fi. Somebody is unmuted. So, and that kind of brings us to where the two things meet, which is to realize the goals that I laid out before for 5G. The cellular network is going to have to rebuild itself, and it's going to do that using cloud technology. That's going to be bare metal servers and switches, microservices, cloud native software, and agile engineering practices. So everything cloud is being applied to the network. So this is the punchline, if you will, to what we're going to spend the next couple of hours talking about. And we're going to work through the process of arriving at this. But this is an example enterprise, and they've got a little edge enterprise cluster, and you can see all the different kinds of devices that might be connected to it. And we're going to assume that in the enterprise, we're deploying small cells. CBRS in the US would be the spectrum that we're going to use. And we're going to treat it as a cloud service. I mean, everybody understands cloud services. You log into your portal in the cloud and you control what's going on in your enterprise from the cloud. So what is this thing that we're controlling? Well, 5G has a control plane, and we can put most of that control plane in the cloud. We don't have to have it on-prem. What's on-prem? The 5G data plane. Now, 5G doesn't call it the data plane, and we'll tease that apart, but just in very generic terms, the control plane lives in the cloud, 5G, and the data plane lives at the edge. That's very SDN-like as well. What this is sometimes called as local breakout, that I can now use the data plane to communicate over 5G without ever leaving my premises, leaving my enterprise. Now, there's going to be apps running in the cloud, central apps, and there's going to be other apps at the edge, because I've got a cloud at the edge. And so now the whole point of this is I can have these different use cases communicating with the edge apps most of the time, and whenever they need to go out and do something more complicated, they can. So this is what we're going to explore and build and sort of deconstruct and then put it back together again. This is a real system. Not only is there real software, it's an up and running system, and it is being used by researchers. And the whole point of this tutorial is to give you an introduction to it, show you where you can go learn more. And if you see an opportunity here, there is a real deployment here that you can take advantage of. So I'm not going to spend time here, but there's position papers on what researchers of opportunities are. There's 2 projects here. Ether is the name of the substrate, the edge cloud substrate. Pronto is a research project that Nate and Jen and others are involved in using Ether as their platform. And so we'll talk about those research opportunities. And like I said, everything that are in these slides, if I go through something too fast and you want to know more, go take a look at those 2 textbooks. So with that, let's jump into the architecture. And Jen, Nate, Oz, if you need to flag me down for anything, or you think I just need to take a breath, speak up. Okay, so let's go. I'm going back to the picture I showed you before. Tens of thousands of cell towers make up the cellular network, and they're aggregated back in central offices, sometimes called. But so let's deconstruct this, and we're just going to focus in on one of these and blow it up. And this is to make the first point, which is simply that when you talk about the mobile network, there's really 2 pieces to it. One piece is the RAN, the radio access network. That's the base stations interconnected by some backhaul network, speaking over the air, radio on the radio spectrum to devices. And there's the mobile core, which is basically the gateway connecting the RAN to the backbone. That mobile core is a fancy word for, it's an IP router. Now, there's a lot of terminology in here, and I'm going to try to avoid using all of it. One of the unfortunate things with the 3GPP standards for the cellular network is that every generation that comes along, a new set of terminology is introduced. So you can see some of it here. I'm going to use the generic term base station and mobile core, although I'm specifically going to be talking about the 5G variation of it. So just another word about the mobile core, because we're going to probably spend most of our time, not entirely, but most of our time on the RAN. It's basically an IP gateway. It looks like a gateway, right? It's speaking out the backhaul network to the RAN, and it's speaking the other direction IP back to the internet. So it provides IP connectivity. It is typically, and because it's an access network, it's where you would shape and enforce some level of queuing on subscribers to get QoS. So there is a QoS aspect here that you might not find in your campus Wi-Fi. And it's also probably unlike your campus Wi-Fi, where you're gonna track usage for the sake of billing. Now, the thing that's above and beyond other kinds of access networks is clearly there's mobility, and the mobile core tracks mobility, because if someone wants to call your number and you've moved, the mobile core knows where you currently are, which base station is currently serving you. It isn't responsible for mobility, the base stations are, but it's tracking it so that you can tell the rest of the world about it. So what I'm going to do in a few slides is explore the architecture of the mobile network from the point of the components in the network. This would be kind of like trying to describe to someone the internet by describing a router. And it's one way to do it, probably not the best way, but it's a good starting point. So the first thing is that we're going to separate the control plane from the data plane, except mobile network calls it the user plane. But you can substitute data plane anytime I say user plane. And that's true for both the core. There's a core control plane and a core user plane, data plane. And I've got 2 little compute boxes in the base station because there's computing there as well as the antenna. And there's a user plane and a control plane there as well. So I'm going to do this from time to time. It's sort of like you are here. So we started out with the 4G, 5G mobile cellular network, but it's really got 4 parts to it. Control plane part and the user plane part in one dimension, and RAN core in the other dimension. So we'll start breaking these apart. But what I'm going to do is go into primarily into the base station for a little while here. So the first thing the base station does is it detects UEs. That's the one acronym I'm going to use. The UE is the device, user equipment. The UE detects UEs when they come online or come within range. And when it detects a UE, it sets up a control plane. It has a control plane connection to connect that UE to the control plane so that we can manage this particular subscriber and figure out what to do with him. it also sets up the user plane. And you have to remember, of course, that the mobile network was originally used for voice. Data was introduced in 3G. And so there's a channel, if you will, logically, a slice for voice traffic, and there might be another one for broadband data. In 4G, that was basically all you had. In 5G, that's going to generalize. There can be multiple slices of the data of the user plane slices that I can use to communicate for different levels of service, different QoS. And it just so happens, and again, this is a lot of the things that are kind of messy about understanding what goes on in the mobile network is because it evolved over time. And so it originally was circuit-based, not IP-based. Then it became IP-based, but it's IP-based based on tunneling. So there's a tunneling going on. And it's not until you get to the over-the-air interface that you're actually breaking these IP packets that have been tunneled to the base station into little fragments, segments, and then you're transmitting them. That's one base station, but the base stations are connected to each other. They form, the way I think about it is the backhaul network that connects the base stations is really a substrate. And the connection of base stations is an overlay on that. And so they're all connected to each other as well as back to the mobile core. And so one of the things, of course, they do is these base stations talk to each other and agree to hand a UE off from one base station to another. So it's the base station responsible for handover. They also can do link aggregation and load balancing. The cells overlap. There will be different times, the different moments in time that multiple base stations could serve the same UE. They can decide literally to link aggregate, they both transmit to it, or they can decide based upon how busy each of them is with other work that they're going to load balance in one way or another. So it's not strictly who signals the strongest. There's a huge amount of intelligence in deciding how these base stations cooperate with each other to get the best use out of the spectrum that they're trying to manage. So one takeaway from this is I think of these base stations, look at the dotted line I've got drawn, there's a base station. Think of that as a packet switch. It happens to have an antenna attached to it. So at one of its ports, it speaks radio, but the base stations are connected to each other to form a packet switch network overlay. They route packets to each other and they make decisions as to which base station is the appropriate one to deal with a particular UE, and that changes over time as UEs move and other UEs move into their cell, and so they've got work to do, so they hand it off. But think of it as a packet. So what we've got now is I've already skimmed off the acronyms. Base stations are packet switches and the mobile core is an IP network. And if you start to think of it that way, then everything you know about networking now applies. So looking at the mobile core for a second, and I'm going to look at the 5G version of it. Again, it's got a user plane piece and a data plane piece, or a control plane. It is basically a service mesh. It's a set of microservices. And if you look at the standard, it's not literally claiming these are microservices because no standard would ever prescribe an implementation, but it's crafted in a way that there's a natural implementation as a set of Kubernetes microservices. And I'm not going to go into the detail. I can say that even though they've assigned new acronyms to several of those are building blocks that you would recognize. There's a directory service. There's a SQL database. There's an SQL database. There's a message buffer. It's everything you're familiar with if you've ever built a cloud service from a set of microservices. That's kind of the foundation, on top of which there's three things. Well, first of all, there's the UPF, the user plane function. That is the data plane. That's the IP forwarder. And then there's three control functions. One is managing mobility, one manages the session, and one is responsible for authentication. And I mean, we're going to talk about those as functions and not worry about the acronyms, but those are the three basic things that the core and the control plane has to deal with. And like I said, the UPF, if you add some queuing to it and queue management, QoS, it's an IP router. So let's look at the sequence of steps that happens when a UE connects. So first of all, this is partly about security and it's partly about address assignment. So there's a secure, the base stations are connected to each other. I'm only showing one base station here. The base stations are connected to each other and back to the core on a secure private network. So that's the first assumption that you're making. The second assumption you're making is that there's a SIM card in every UE. And that SIM card has the unique identifier for this UE. Again, unique identifier, it's kind of like, I kind of think of it like your Ethernet address. It's your MAC address. It's unique to you no matter where you plug in. And then you get assigned an IP address. Again, conceptually, that's the way I think of it. It's also got a secret on there that's going to be used to authenticate this UE to the carrier. And information about what bits of the spectrum and how to encode on the radio, everything you need to know to talk to your provider. So step one, the UE connects over an open channel to the base station. This basically is, I'm here. As a consequence of that, because there's a secure path between the base station back to the core, I'm now able to, the core is able to authenticate the UE. So there's an authentication protocol that would be, very familiar. There's different implementation options, but the core can authenticate that this UE is in fact who it claims to be based upon the secret in the SIM. And as a consequence, looks that user up in a table and says, and does IP address assignment. So it sets up the user plane. So it does IP address assignment. It goes to the user plane and says, I'm going to give this UE IP address XYZ. It goes to the base station and does the same. And to both the core and the base station down on the user plane, it's setting up all the QoS parameters that I'm going to need. So that I can, get my level of service out of this particular network. And it goes to and tells the UE everything it needs. So at this point, the data plane has been set up. I've been assigned an IP address, and everybody and the queue assignments are all there. I've looked you up in my subscriber database. I know what kind of service to deliver you, and everything's good to go. And I now have a user plane channel established. And you can generalize that if you were to have in your subscriber profile that you had different data plane channels, user plane channels for different purposes, and then connecting, this application gets to use this level of service, that application gets to use this other level of service. That is all part of the 5G setup. So this is how you connect the first time. If the UE moves, as long as it's reaching a base station serviced by the same core, the session manager will maintain the session and your IP address will stay the same. If you ever leave the core because you've traveled from New York to San Francisco, not only probably did you turn your phone off because you're on a plane, but you will get assigned a new IP address. But as long as you're being served by the same core, and just to a first approximation, think of a core as a large metro area, you will move seamlessly without losing your IP address and in principle without losing any packets. Okay, so those are all the building, the functions, if you will. You've got a funky switching function in the base stations. You've got an IP router augmented with access. You've got access control because you're at the edge of the network, and you've got a SIM card in the UE. So those are all the basic pieces.
So Larry, one thing maybe we should add is the mobile core user plane egress is called a packet data network, and there could be multiple packet data networks. And there is going to be an IP address for each packet data network that you connect to. So at a given time, a UE will most likely have multiple IP addresses.
Yeah, thanks. Good. Okay. Jen, Nate, anything else at this point? All right. All right, good. All right, now I'm going to spend just a very few minutes talking about the over-the-air interface. And again, I'm coming at this as someone who is trying to build and think about how to build a network using cloud technology without trying to dive into the deepest details about the coding theory and information theory. I'm going to trust that someone there's lots and lots of people doing that right. But I want to understand at the abstract level, what is it that's interesting and unique about what happens at the radio edge? And so, again, this is what struck me as important to understand. And so, first of all, it's important to understand how messy this world is. And I think everybody understands transmitting over the radio, you're getting signals bouncing off of different structures. This is largely radio outdoors, especially. And you've got the same signal showing up at the UE at different points in time. And depending on the environment, urban and rural, you can bound how long, how out of sync these things can be. So that all plays a role in how efficiently I can use the spectrum. But the thing that strikes me here is when I send a packet over an optical link, I'm pretty sure that it's going to make it to the other side. And I'm pretty sure I understand with what the error rates are and so on. This is an extremely dynamic thing. So I have to do packet scheduling cognizant of how efficient the medium is in transmitting those packets. So it's more than just saying this packet in a priority queue. I have to adjust everything based upon how efficiently I'm able to use, I being the base station, I'm going to be able to use the spectrum to talk at that particular UE, and I have to do that for the entire set of UEs. So with that kind of understanding, the big takeaway that I have here is that I have to have constant feedback from the user device back to the base station. So, and it's called the channel quality index. It's the signal to noise ratio, so that I can understand and how to best utilize that spectrum, the spectrum that I'm transmitting over. So this quality index is sent back to the base station from every UE every millisecond, and it goes into the computation of scheduling based upon how I'm able to reach each of the many different UEs I'm talking to. So at that point, with that little bit of understanding, yes, there's coding. Yes, there's modulation. The modulation that gets used is for basically 16 QAM or 64 QAM, which the way I think of that is there's signals, they're either 4-bit symbols or 6-bit symbols that I can transmit in any time unit. And yeah, so certainly I code the data, I put some redundancy into it, I modulate it to get so many bits transmitted per time unit. And for me, then it all comes down to, well, how did you multiplex? How did you share that spectrum between all the different subscribers that were trying to use it? Well, 2G, it was time division multiplexing, 3G, CDMA. It's orthogonal frequency division multiplexing multiple access in 4G and 5G. And the way that I visualize that is, and I'm not the only one, I didn't invent this visualization, but it really helped me understand what's going on, is I am basically transmitting symbols in time across the x-axis, and I'm using different sub-frequencies, subcarrier frequencies, to basically create a grid that's available to me to transmit at any given point in time. Now, I'm showing an interval of a millisecond because I can adjust my scheduling of these segments once every millisecond, and based upon the feedback that I get from all of the UEs. And I'm showing 180 kilohertz worth of frequency here, but any given band may be 100 megahertz, I'm sorry, available to me. And so I can divide this grid of capacity that I'm resource allocating is certainly, it goes to the right in time, and it can be much taller in the frequency. And so basically I'm allocating these little time units, and this particular set of numbers comes from 4G, where there wasn't so much flexibility, but in this given time unit, I can transmit one symbol, and that might be 4 bits, it might be 6 bits, but I can transmit that symbol using 15 kilohertz of the spectrum and 1 unit of time. So scheduling, I want to this is my abstract view of scheduling, because now as I build out the rest of the system, I'm responsible for controlling this. And so I want to understand it at this level. So this is the thing I'm trying to control. And so you build a scheduler is the next thing you do. There's actually 2 bits of input to the schedule. Well, 3 bits of input. The first is a set of queues for all the segments that I'm going to transmit to fill out those little resource blocks. And I'm going to have them per subscriber or per class of subscriber. And the scheduler then certainly is servicing this queue, and it's filling out, it's allocating resource blocks to all of those subscribers. And these are little segments, right? These are not IP packets probably, but they're the segments that fit in those little resource blocks. And so you're going to have to segment this, obviously, and then reassemble it at the other end. But the 2 bits of input that the scheduler takes is it's taking the quality index from the channel quality from the users, and it's taking the QoS assignment that I have assigned to this particular user. And that's basically what level of service do you want? And so we'll see some examples of that later, but I can guarantee bit rates, I can guarantee latencies and so on. So I take a QoS parameter, I take a quality parameter, the scheduler then does assignments of all the segments for all the users based upon that. Now, this is a real-time activity, but this is the 5G version of a packet scheduler that you might be familiar with on a wired link. This is the variation of that. Yeah, so these are I'd forgotten that I had the QoS class index is what the acronym stands for, and I can do guaranteed bit rate, delay critical, and so on. And I can give you different specs on error rate. So the 2 big ideas in 5G. One is I'm going to implement most of it in the cloud with cloud technology. That's what we're going to focus on. But the radio is itself quite innovative. So 4G permitted just one waveform. There was one shape to that grid that I had before. 5G is going to allow multiple waveforms. And one of the degrees of freedom that the scheduler has is to change the waveform to meet the QoS requirements of all of the users trying to use that bit of spectrum. So I showed you 15 kilohertz before. It can be 15 or 30, and I can change the scheduling intervals. This is going to be important because it gets me closer to real time. This is for sub-gigahertz bands. For the mid-range bands, there's 3 waveforms. So again, the numerology is changing here. The sub-carrier frequency size is changing, and the intervals are changing. But those give me ranges. It's not a fixed grid. It's now a fungible grid that I can a flexible grid that I can reshape. And then for the small cells, it's even tighter scheduling intervals. I'm making a scheduling decision every 150 microseconds. So qualitatively, the schedulers are able to change the waveform to achieve better channel utilization. Super wide bandwidths enabled the high throughput. Shorter scheduling intervals mean that latency is more predictable, and that's important for mission critical. And there's going to be some narrow bandwidths also set aside for simplified air interfaces. So, like I said, qualitatively, the radio is a significant advance here. But from the point of view of how to build a network, given that, it all comes down to controlling the scheduler and how you define interfaces to the scheduler and how I talk to the scheduler to instruct it as to how to best utilize the resource. Any corrections or qualifications there?
Nope, it's all good.
Okay, so this is where I think things are going to get in. For me, things get interesting, these next 2 sections. Well, I already mentioned that the core is now open source, and it's implemented as a set of microservices. And we're going to take advantage of that fact. There's open source out there, and we're going to use that. I'm not really going to, this is not a tutorial in microservices, so I'm not going to explain how you do that. It's pretty standard stuff. But the RAN is different. So let's go into the RAN. So this is the Rend Pipeline or the RAN protocol stack, depending on whether you set it on its side or you stand it up. I happen to set it on its side, and apologies, the antenna is now on the right and the mobile core is now on the left, but it's basically flipped it from what I had before because I like to work left to right here. So the user plane, the core is sitting off here to the left, and there's a control plane that talks to the control plane counterpart in the RAN and in the base station. And the user plane talks to the user plane part of the pipeline. And not surprisingly, the control plane reaches out and controls each of the stages in this pipeline. So what are these stages? Well, I'm not going to talk about the D to A conversion and the RF front end. Let's just assume that those interfaces to the over-the-air transmission are there. There's a physical layer. We all understand the physical layer. That's where the coding and modulation takes place. And if we step up from there, there's a MAC layer, just like you have in an Ethernet. It's where you schedule and multiplex the segments, just like in Ethernet has an algorithm for sharing access to the wire. This is where you schedule and multiplex access to the air radio. There's also a very late forwarding decision here because I can have multiple physical layers at different frequencies sitting underneath the MAC layer. We're not going to talk too much about that, but one way ultimately you can think about this is if I have different pieces of spectrum, they're each going to have their own PHY layer below the PHY layer and below. Or this is one place that you can unify Wi-Fi and cellular, that I could jump off to the Wi-Fi path if I wanted to share. But I'm not going to spend too much time there. Let's go up the stack. There's a radio link layer. Very familiar. That's where you do segmentation reassembly. And that's where you retransmit any segments that didn't make it through. That's a very familiar network function. If you pop up from there, it's a kind of a grab bag of functions here, but the packet conversion layer it'll do header compression. It is where I do integrity check of the data that's being transmitted. And most importantly, that's where you'd make an early forwarding decision. If you decide that you're not the base station to handle this because there's control logic that said we should pass it to my neighbor base station, that's where that pass off handover happens. So there is a forwarding link that comes out of that. And then finally, the control piece configures and sets all the policy related aspects of the pipeline. Now, that's a coarse grain near real-time control. The scheduler that runs in the MAC is the real-time control. So making note that I can, even if the user plane believes that this particular base station is the right one to send to a particular UE, it's at the point it reaches the PDCP that it can make a routing decision, if you will, and forward to it, and/or link aggregation or load balancing decision to pass it off to another base station. And again, I mentioned the other carrier frequencies could be there too. Historically, up until now, this all runs in the base station. So this is sort of, I'm drawing a lot of parallels to the way you think of switches. At one time, switches ran both the user plane and the data plane, and it was all bundled together. And then we started that disaggregated. That's what we're going to do here. But this all historically runs in the base station. They're all each standalone packet switches with radios attached to them. All right, so what we're going to do is we're going to disaggregate this. We're going to bust it into pieces. And there are a lot of motivations for doing this, which we probably aren't going to have enough time to get into here, but there is a carrier-led organization called the Open RAN Alliance, ORAN. This is in addition to the normal traditional standards body, the 3GPP organization that standardizes the cellular network. This is that's typically vendor-led. This is an operator-led organization that is basically trying to get out from vendor lock-in. And one of the ways they've done that is they've taken the available interfaces and they said, we're going to subdivide this. We're going to have a central unit that comprises these two components. We're going to have a distributed unit that is the next two units and a little bit of the PHY. And then we're going to have the radio unit that's the bottom analog pieces. And we're going to split the RAN there. There were different split points, but this is the one that the carriers leading the ORAN organization was originally formed by AT&T and China Mobile, two of the largest carriers. And Sachin, I don't know if he's on, was right in the middle of all of this. All right, so once I've done that, I don't have to put it all on the base station. I've got user and control plane elements in the CU. So we're going to separate them out. There's the CU control plane, the CU user plane, CUC and CUU. I'm going to introduce my own acronyms. And the DU clearly needs to be fairly close to the RUs because that's where the scheduler lives, and the scheduler can't get too far away from the radio units. It could be in the same cell tower, and that very well could be the case for macro cells. But when you go in the small cell direction that you might deploy through your campus or your enterprise or your manufacturing plant, then you might have one DU connected to many RUs, and that DU's in close proximity. So instead of the set of cell towers that I had in earlier pictures, the world now looks like this. The CU runs in the cloud, servicing a set of DUs. DUs each serve a set of RUs. We've split and hierarchically distributed the RAN instead of bundling it together in the base stations. All right, so having done that, let's come back and revisit how we can structure the software to make that happen. I've removed the split annotations overlay here. I'm going to focus on the RRC, which is the control plane. It's responsible for near real-time control, whereas the scheduler in the MAC stage is responsible for real-time control. All right, I've just drawn it slightly differently. And the reason I did that is I'm going to break the RRC into two pieces. One piece is it's still the standard interface back to the mobile core. So the mobile core doesn't know whether I'm pulling this trick or not. I'm still talking to the mobile core in the 3GPP standard way that I always have. So I can plug any device in here. By the way, if it's a little confusing, the control plane may communicate with the UE by sending control packets through the user plane. So that's why there's a blue edge that comes down to the user plane. The thing that I carved off and broke off of the interface that's now actually responsible for controlling the stages in the RAN pipeline is, we're going to rename it. It's near real-time RAN intelligent controller, or RIC, near real-time RIC. This is terminology from the Open RAN Alliance. And you don't have to squint very hard to recognize what that is. It's an SDN controller. And so I'm going to take you down a path where we are going to implement the RIC as a network operating system, and network, like all network operating systems, it has a database of state about the network it's managing, and it's running a set of control apps. So this is SD-RAN in one picture. Those control apps can set slices up on behalf of different quality of service classes. There's certain configuration things it can do. We weren't going to focus so much on configuration, but it can do runtime control of the RAN. It can control the link aggregation. It can control interference management, because these base stations and radios have the ability to turn their power up and down, and they can interfere with each other in different ways. You can control that. You can control load balance. You can control handover. So there's a set of control apps. ORAN calls them X apps, but they're SDN control apps, and it runs on a network operating system. That operating system is collecting in a database, or a RAN NIB, network information base, not the real-time data, but running averages, time averaged values for all of the signal to noise information that's being collected from the devices, those CQI values. And it's reaching out and it's controlling all the RAN stage pipelines, but in particular, it's controlling the MAC, which is where the real-time scheduler runs. Now, the MAC is talking to the individual UEs in real time, that 1 millisecond latency bound. And so it has instantaneous values, so it can make its real-time decisions, but I can pass up summaries of that information into the network operating system. And I can do that from all the base stations, right? All the DUs and RUs. And I can aggregate that information, and then I can make a globally optimal decision in these control apps based upon the global information I have available to me. So this is where RAN is headed. It's going to be a software-defined RAN. Am I doing on time here? Okay, pretty good. So let's do another one of those "you are here" slides. So we know that the mobile network has 4 parts. And now we have sliced or split the RAN. So it's not, the RAN isn't just one column. It's now the RU, the DU, and the CU. And the CU is where the control piece lives. And so I left the CUC and the CUU there. And if I were to focus in on the RAN CUC, it is now responsible for controlling the RU, the DU, and the CUU. And if I drew that picture differently, it looks a lot like an SDN picture, and that's what we're going to get to in a few minutes. It's the controller and a set of apps. There's more coming, and the more coming is I'm going to go into the user plane, and I'm going to split that into a control and data piece. Now this is a little confusing, but the entire cellular network is an overlay on top of underlay networking technology. The backhaul network might have been Ethernet. It might have been fiber-based, this or that. And so I can actually go into the switches and program some of the functionality. I think it'll be clear when I go through the example, but this is basically the user plane of the mobile core is the UPF, the user plane function. That piece can be subdivided to have a control component and a data plane component. And the data plane component I can put into a programmable switch and program it in P4. So I'm going to take a little detour in just a slide to show you this. It happens to be one example of a bit of research. There's a paper going to be at SOSR describing this that one of Jen's students is working on in collaboration with some of the engineers at ONF. And yeah, it's how do you implement this functionality in P4. So let's look at that just for a minute. And again, this is just a little illustration of an example of where there's a research opportunity. So this is just to remind you where the UPF sits in the big picture. It's the data user plane piece of the mobile core. So I was in the RAN, I've come back to the mobile core, just hopefully help you keep that straight. So I'm just going to blow it up. And to the right is the internet, and to the left is the radio unit. And I'm going to use a combination of software and hardware. I'm going to implement this with a programmable switch. So everything, hopefully, I'm going to drill down into this in a few slides, but the mobile, this P4 programmable switch that you might very well be familiar with is basically the switch I'm going to program with the UPF functionality. All right. I'm going to attach it to a server, and I'm going to attach it in 2 different paths. So the control plane lives outside here. Remember, this is all user plane. There's a little control agent that sits on the server. I'm going to connect a smart NIC and a dumb NIC to it. And the dumb NIC, I'm going to run virtual switch and software on top of it. I'm calling these different opportunities out because they're in parallel. You can play with all of these. The switch is P4 programmable. The smart NIC is P4 programmable. The dumb NIC is not, but the virtual switch that runs on top of the smart NIC is. So there are 2 possible data paths through here. One of the data paths goes to the dumb switch and implements the UPF functionality in P4 running in the virtual switch on the server. And the other is the quote unquote hardware path that runs, it gets diverted to the smart NIC, but a lot of the behavior and that's an FPGA-based NIC right now. The rest of the behavior is implemented in the programmable switch. These are the prototype work here all happened with Intel barefoot Tofino switches. Yeah, so what is it they had to do? Well, they had to forward IP packets. But before they could forward IP packets, they had to deal with the tunnel information headers that have been attached to it. So it adds and strips headers because to talk to the radio units, you have to have the GTP tunneling information. You can also implement the QoS that you need to offer different levels of service to different subscribers. This is class-based. It's not a queue per subscriber. we don't have that many queues available, but it's a queue per class. And then you can do admission control to a given class to be able to assure them that they're getting level of service they had paid for. Unfortunately, today's programmable switches can't do everything that you needed to do. The other piece is extra buffering. And this is extra buffering in the sense that when a UE moves from one base station to another, and the base stations agree that that's going to happen, there's a period of time as they alert the mobile core about that mobility that there are packets still arriving, and the standards for the mobile network are such that they do not want to drop those packets. If you were thinking, I move my laptop, if I lose a few packets, I'll just retransmit, no big deal, because I was doing TCP anyway. That's a reasonable way to think about this. And I think there's an interesting research question in whether this buffering, the role this buffering really plays in broadband data communication as opposed to voice, which is what originally motivated it. Oz and I have spirited debates about this, but I think there's an interesting question there. But the point is that the buffering is implemented in the SmartNIC because there's more buffering available. So most of the packets can be forwarded through the programmable switch without ever hitting a server. If I'm in the state of having to deal with multiple mobility between different base stations, then I send it to the SmartNIC for buffering. And like I said, if you go to the book, there's a link to this paper. You can go read the paper for more information. But I wanted to give you that as just a little teaser as an example of what one can do once you jump into this software. So that's the end of this. Yeah. So I've got a few more minutes before the break. I'm going to jump into the next bit of material, but let me stop here and give my colleagues a chance to speak up for a second. Yeah, I'm actually going to switch over to another deck. So Oz, Nate, Jen, have at it. They may have stepped out.
We're here. Oh, sorry, we're gonna have weird feedback. We're sitting next to each other at the hotel. Was curious if you could just tell us a bit about some of the killer apps for RIC programmability. That'd be cool to hear about.
Well, yeah, so it's a good question. So I mean, for starters, there's the sort of the first thing you do is you achieve parity with. Sorry, yeah, there we go. You achieve parity with what you had before. So is there innovative work to do in handover control? There's algorithmic work there. And so maybe you implement basic handover and then you enhance it. And you discover how it falls short. I see Oz is there now. Maybe he can. I'm kind of just split focused here for a second.
Sure. So effectively, when you think of the RAN, there are three hierarchies of control that you can do. One is geography-based. So it is not a single base station. It is a group of base stations that you program all together towards optimizing the overall performance across geography. So an example for that would be load balancing, for example, right? And then there is the base station specific control. So there, for example, link aggregation, carrier aggregation, and traffic steering are good examples for that. And then the next one is the UE-based control. So there, for example, you could talk about slicing the mobile link and adjusting the quality of service parameters for a given session towards enabling a performant UE operation.
So Nate, another whole dimension to this is, and that's what we understand today, but now with 5G, I've got massive increase in density. I've got massive increase in bandwidth, and I've got really stringent latency guarantees I'm trying to make. That's whole new space. We don't know how to do that. We just know we want to do it. Anything else before we? Okay. So the next little session here, and then we'll take a break. Is
Hey, Larry, do you mind if I throw in one more question? Maybe
Yeah.
this is one more for Oz than for you. I mean, when you think about writing applications for the cloud, you tend to write them differently, you know, with a separation of state and control logic. And so I'm just curious to what extent cloud principles go into the creating of these, you know, decoupled pieces of software.
So excellent question, Jen. So bringing cloud native to mobile core and RAN is an active research area. When you think of the mobile core control plane, for example, there are a lot of microservices. There is one that handles authentication. There is another one that tracks mobility. There is one that does session control, and all of those, as you can imagine, will have a significant amount of state that they maintain internally. But because they're stateful, plain containerizing them is not sufficient to enjoy all of what cloud brings. For vertical scaling, etc., you need to be able to disaggregate the state maintenance. So 5G as a standard has actually, at least from an architectural perspective, has laid out the groundwork for how that could be done. There is actually a mobile core function that it has defined, which is all about a data store for state maintenance, and that is accessible via REST interfaces. So, but having said that, in today's 5G implementations, very few, if any, have gone all the way to cloud native. So that is definitely an active work and research area.
Yeah, I'm going to repeat myself, but those objectives at the front end were just unbelievably aggressive, and everyone has different philosophies about how to conduct research, but when I see objectives like that and open source microservice-based versions of this software is just now available, that's just a ripe field to jump into.
I mean, one thing that I can say, I know that you are going to talk about open source. So within ONF, the open source 5G core that we have, by end of this year, we'll have two of the most important control plane components completely cloud native. So the session management and mobility management components.
Good, thanks. That's a great point. All right, so what I'm going to do until a break is, you've seen it coming. We've disaggregated 5G in a way, the RAN in particular, in a way that we can bring SDN principles to it. But I'm not doing that in the abstract. This is happening, being engineered. There's software on GitHub. You can download it, you can run it, but I need to sort of walk you through what the building blocks are. And so this is a little bit of an SDN primer, but I'm going to hope that you've had enough exposure to SDN that it's all going to make sense. This is the 10,000 feet view of SDN, right? There's a network operating system. It maintains some global state, some control apps run on top of it. It reaches down into a distributed data plane and touches all the switches and programs them through something like flow rules or P4 runtime. But in reality, networks aren't just these pretty pictures of switches in that particular topology. They are they tend to be much more stylized. So the first dominant use case of SDN is by the cloud providers, and they've taken the leaf spine switching fabrics of their clusters and they've made them SDN controlled. I'm not showing the software, I'm just showing the configuration of the switches, right? Leaf spine. And clearly this is a little tiny data center, but it serves, it's going to be sufficient. So the functionality that gets implemented here is everything that you needed to run workload, Kubernetes workloads or whatever, virtual machine workloads on a cluster. It's got L2 within rack. It's got L3 switching between subnets, between racks. It's got Q and Q, nested, doubly tagged VLANs. It's doing IP routing, IPv4, v6. It's doing multicast. It's discovering what hosts are connected. And it's built in a highly available way. And again, I'm just trying to emphasize, this is a soup to nuts SDN implementation of a widely used use case. And again, major, the Googles and the Microsofts and their clouds have been running this for some time. It's well understood. Well, let me show you another use case. Let's take that same cluster, and this time it's maybe adequately sized because we're going to run it in your enterprise at the edge. And we're going to connect the backhaul network to a set of base stations and radio units to one end, and we're going to connect to the internet out the other end. That is the 5G enabled edge cloud. It's another use case for SDN, but this is the particular configuration. So again, this is the combination of it's a cloud and it's the implementation of everything related to 5G. And what we're going to do is we're going to see what those other pieces are. So if we look, so I'm going to show you the stack, and we're going to start at the hardware level. So at the hardware level, we're going to assume our building block is a programmable switch built out of merchant silicon switching chips. And we're going to run an operating system on the switch, and that operating system is going to export an API that we can use to control and configure the switch. The next layer up the stack is a network operating system. Now it's servicing multiple switches. I'm just showing sort of the vertical cut of the stack. That operating system has a northbound API. And there's going to be a set of control apps that run on top of that. So this is now a slightly more precise version of the picture, my 10,000 foot picture. And let me make it even more precise. We're going to define an API. It's going to be gRPC based, and it's going to be GNMI, GNOI, which is configuration interfaces, and P4 runtime and OpenFlow will be my control interfaces. And we're going to put an operating system there. ONL is Open Networking Linux, and Stratum is an API layer that's layered on top of ONL. And we're going to run this on real switching hardware. It's going to be the barefoot-based Afino switch. So what I'm trying to take, we're taking you on a journey now, drilling down. This is real. You can go buy these parts and you can assemble these pieces together. The operating system is also, the network operating system has a northbound interface, flow objectives. It's kind of a pipeline independent version of OpenFlow, kind of. Probably ought to be P4 runtime, but it's not quite there yet. And the actual software piece is called ONOS, the Open Network Operating System. Stratum and ONOS are ONF open source projects. On top of that, we're going to run a suite of control apps that collectively are called software-defined fabric. And it's not just implementing that feature set I had a couple slides ago. It's also it's an access-ready leaf spine fabric that it's built in such a way that I can plug the RAN into one of those leaf switches. Then there is a full tool chain associated with P4. So there's a P4 compiler that can take a specification of what runs on the switch, fabric.p4, and an architecture definition for the switch, which in this particular case, it's the Tofino network architecture, TNA. If this isn't familiar to you in this level of detail, one of those open source books drills down on all of this. So go take a look. All right, so this is kind of just a simplified version of that stack. We deploy that stack on the hardware configuration from the previous slide, and now it looks like this. So we have ONOS controlling a leaf spine set of fabrics. Stratum is running on each one of the switches that build that fabric. One of the leaf switches is connected to the internet through a standard old core router. And SD Fabric is again, it's a set of apps. It's not a single app. There's one responsible for topology management. There's one responsible for multicast, one for setting up routes, and so on. Fabric.p4 programs the data plane in each one of these switches. And now I'm going to plug my RAN into one of those switches. So the radio access network is a set of these cell tower, the RUs. And I'm not showing the disaggregation here. Generalize the blue cloud, that is the RAN, to the full split version that I had before. But the important point is, in the same way that I have OpenFlow and P4 runtime as options for controlling the switches in the switching fabric, I need to also control the RAN devices. So there is a control interface that's being standardized for RAN devices. Think of this as the RAN version of OpenFlow, but it's specific to these RUs and DUs and CUs that I was talking about before. There is also then a set of control apps. So the fabric is a set of control apps to control the switches in the switching fabric, and SD-RAN is a set of control apps that control the RAN elements using the interface that I've not given a name to, but it's being standardized by the ORAN. So this is now the stack that we're going to deploy. What I want to do, so each of these components, again, you can go learn more detail about, but I wanted to blow ONOS up a little bit because it's a critical piece of all of this. So ONOS is a network operating system. It's built as a horizontally scalable service, which is to say it has a distributed core, runs on multiple servers, probably in the cloud. That core is built from a set of modules, or they're sometimes microservices, sometimes not. A lot of it's implemented in Java, and these are Java modules, but it's highly modular, whether it's microservices or not. So there's a module in there that manages topology. There's a module in there that discovers hosts. There's a module in there that manages configuration and so on. And all of that, because it's a horizontally scalable service, is stored in a key value store. On top of that, there's a set of northbound APIs. And notice the ... here. We can add more northbound APIs to deal with what the control apps in the RAN case need. These are just generic control apps. And there's a set of southbound interfaces. So this is where OpenFlow talks to the switches, P4 runtimes talks to the switches, and so on. And again, ... if these switches are replaced with RAN elements, then there's a southbound interface. So what we're doing, this is ONOS generically, and it's how we control the switching fabric. But we could take this same framework and slightly reconfigure it, and we can build the RIC that I talked about before. So the RIC is not just there in the abstract. There is a RIC, a RAN intelligent controller, implemented in ONOS by using many of the pieces that were already there and then adding the pieces that were missing. So there's a RAN telemetry service. That's basically taking all of those quality values back from the RAN elements. There's a control interface that's deciding which base station or which RAN element is dealing with UE and how things are handed off and links shared and so on. So that's stored in a key value store. The telemetry data is stored in a time-shared database. And all the other services that were already there that I can reuse, I'm reusing. So the topology service is being reused to manage the backhaul network that interconnects all of the base stations or the cell units, radio units. So there's a new northbound interface that interfaces to the non-real-time orchestration that lives up above. There's always going to be a management layer that gives me my configuration, and that comes in through an interface that is being defined, standard interface that you can build management services and talk to this. On the southbound side, there is an interface cryptically named E2, but think of E2 as the RAN version of OpenFlow. And by the way, anytime you've got an interface like this and a new set of elements that I'm controlling, I know there's standards work going on here, but in my view, this is a wide open space to get this right. And so I think this is going to be iterated over the next decade quite a bit. And, you know, the ONF team is working with the carriers and the Open RAN Alliance to nudge them towards rational designs here, but there's lots of opportunity there. And then you have, again, this set of control apps that are on top. The other thing that's happening here is I could have called this an API, but it's really becomes a software development kit, an SDK for building X apps. And right now, again, lots of research opportunities there in getting that right, but it's basically just showing the E2 interface through. It's not much more than that. So this exists. It controls radio units, and even though this runs, you know, in a cloud sort of way, it can handle tens of thousands, hundreds of thousands of UEs with very small handover delays. So this is entirely feasible.
Larry, there's a question in the chat from Doug Montgomery. He says RAN version of OpenFlow. He just wanted to know if that's an architectural analogy or is there some actual technical similarity to the interface?
Great question. I'm using that very generically just to help you equate the two. So it's an interesting, that's the end of the slides. This is a great question. There's an interesting dynamic here with the users of the technology, the network operators, wanting to not have vendor lock-in and vendors wanting to have vendor lock-in. So how do you do that? OpenFlow went through the same thing, right? OpenFlow started out as this generic way you could control switching devices, except everybody's pipeline, forwarding pipeline turned out different. And so when you wrote a control app to the OpenFlow interface, it became tightly coupled to the switch pipeline. The same issue raises its head here, which is every vendor has a slightly different definition of what those elements do. And they want to preserve their uniqueness and yet provide a generic interface to control them. So that's the tension, that's the tussle going on here. And right now, if you look in the book, there's a lot more detail, but basically what's happened right now is that the RAN elements get to specify a service model. And then the operations that the apps can perform on that service model are relative to the service model. So it's kind of punted it a little bit. So if you focus in on one of those service models, then it looks an awful lot like OpenFlow, at least if you squint, because you're controlling who this particular element is talking to for handover control, and you're learning metrics from. You're reading metrics and you're writing control. So there's gets and puts in that respect. So it's not literal OpenFlow, but the challenging problem is exactly the same. You're in the middle of this. Maybe you want to say more about that.
Sure. So the way I would maybe pose this as it is not exactly like OpenFlow and it is not like P4, but it is somewhere in between the two, in the sense that the E2 that Larry has on this slide actually has two components. There is the access protocol, E2AP, and then the service model. And the service model is basically the contract between a suite of applications, RAN control applications, and the RAN elements. So every time, and ORAN Alliance standardizes these service models, these contracts. So then any RAN element that wants to be compliant to the standard needs to implement all of the necessary changes into their software stack. So in that sense, it is not really like P4, but at the same time, the service model is sort of like the P4 runtime.
Great. So thanks. Yeah, I think it's incredibly interesting how this is all playing out. And from a system design point of view, it's attractive to me as a place to try to understand what the right primitives are and craft the right abstractions and so on. But it's also snared in a standardization process. So that's the complication here. But what Oz and the team he's working with has been doing is they're implement it first and then use that understanding to help try to drive the standards that's happening. Okay, so we've hit the top of the hour. Let's take a break for half an hour and we'll see you back here. And what'll happen in the next half is I'm going to walk you through the end-to-endness, and we're going to assemble this back into an edge cloud, but we're going to spend most of the time, or at least half of the time, with all of the researchers on the call talking about where they're doing their research. So we'll see you in half an hour.